Hello everyone, and welcome to Siphon. So this video gets pretty crazy, so to explain where it all begins, let me tell you a story. It's summertime, so a couple of friends and I decide to go down to the fair. Now, none of us wanted to pay the $50 for the 5 rides on a kitty teacup mobile, so we were left with two things to do: eat and buy stuff. If you've ever been to the fair, you will know how awful the stupid products they sell are. We passed through so many scams, it was hilarious. Some guy even offered me tamarind as a cure for literally everything. But my eye caught something just as we were leaving one of the tents. It was a deck of cards called the Junkin deck. It was made by a guy named Jeff. I'll put his website in the description if you are ever interested. This deck of cards had an interesting feature, a rock, paper, scissors type system that the creator had made. The interesting thing about that was that this system used 5 different suits. It added on lizard and water, and I used this diagram to show you how the system worked. After doing some more research, I realized that this is identical to the game Rock, Paper, Scissors, Lizard, Spock, which was popularized by Big Bang Theory. So if you know that game, you can think of water as Spock instead. Now, this deck of cards was actually what led me to think of this video. I will say I am probably not the first to think of this, but I think I have a good amount of information to add to it. Now, before I can explain the connection between that whole story and the title of this video, I have to explain to you what a quaternion is. Chances are, if you're getting this video recommended to you, you might already know what quaternions are, but stay with me because there are a few important details in the way I'll be introducing them that you might not have seen. Now, if you've taken a pre-calc course, you might know that complex numbers consist of a real and imaginary part. You can plot these on a 2D graph like so. So what is a quaternion? Well, in the simplest way of describing it, a quaternion is a 4-dimensional expansion of the complex numbers. Quaternions are much the same, but instead of one imaginary component, they have 3 of them: I, j, and k, all of which square to -1. Now, I'm glossing over a lot of facts about this, so if you want a better understanding, I will leave a link to 3 Blue 1 Brown's video on this topic in the description. I am just using quaternions, he really explains them. Now, the most important thing in our case about quaternions is that they are non-commutative. That means that A times B doesn't always equal B times A. To help visualize this, you can see this diagram. Now, if you multiply along the direction of the arrows, for example, I times j, you will end up with the next letter in the sequence, in this case k. Conversely, if you go against the direction, like k times j, you'll end up with the next letter, but negative. So you get negative I. Now, the important thing that you can see from this diagram is that for any 2 different imaginary units, a and b, a times b is equal to negative b times a, right? Since both lead to the same result, but one is against the flow. This property is called anti-commutativity, and it is crucial for this video. At this point, you may be asking yourself, I thought I clicked on a rock, paper, scissors video. What does this have to do with rock, paper, scissors? Well, let me draw the rock, paper, scissors diagram for you, and you might see it. Now, we can see the similarities, right? If we were to say that I is rock, J is scissors, and K is paper, the flow of the quaternion diagram shows what wins against what. Now, when we multiply one player's moves by the other, if the result is some positive imaginary number, the first player in the product is won. If the result is negative imaginary, that player has lost, and if the result is -1, the game is a tie. You can think of this as a positive imaginary would be something like rock times scissors, right? Where I times j leads to a positive result. But conversely, scissors times rock leads to a negative result. That's a loss. Scissors versus scissors, it's just a tie. Now, let's try an example. Let's say I pick scissors, right? And you pick rock. To see what my result is, we start with my move, which was j, right? And then we multiply by yours. Now we have j times I, which is negative k. Since it's against the flow, it's a negative number, and that means that I lost. Now, if we were to go the opposite direction, I times j, as in I picked rock, you picked scissors, we would know that we will get an opposite result, positive k in this case, since we are now with the flow of the graph. This is what we should expect, since if one player loses, we expect the other to have won, and vice versa, and it arises from the anti-commutativity relation we talked about earlier. Now you can see why it's so important that if you flip a multiplication, the sign of the product should also flip. But not all quaternions are just I, j, or k, same way that not all complex numbers are just I. So what about the rest? How do we represent them? Well, just like complex numbers, we can represent a quaternion as a sum of different elements, like so, with our multiplication being represented by this diagram, like before. For our chosen rock, paper, scissors symbol, we can represent them as quaternions with every element as 0 except one of them, like this. This also means that we can represent the result quaternion like this. Now, note that I will be referring to this result quaternion as QR, which is the product of the player's choices Q1 and Q2 respectively, right? So, for example, if we have rock times scissors, the result of the product can be represented as K, like so. So now we can start to see how we can create a formula to test for who won. Let's try a few more scenarios. If we try scissors times rock, like before, we get the same result by negative, as I showed before. And if we try scissors versus scissors, we get j squared, which is just equal to negative 1. This means that if we can somehow get the imaginary component of the quaternion, we can tell whether it was a win or a loss. And if we get the real part, we can test for ties. To phrase this more mathematically, using the quaternion representation, we can make a table of possibilities. Remember that these are the possibilities for the first player in the product. The second player has the exact opposite. So if player 1 wins, player 2 loses. If player 2 wins, player 1 loses. For the first player to win, either B, C, or D is positive 1 in the result quaternion. If the game is a tie, A in the result quaternion QR is a negative 1, and if player 1 loses, one of the imaginary coefficients is negative. We can actually simplify these conditions by realizing that only one coefficient in the result quaternion is non-zero. This means that the value of one non-zero imaginary component is the same as the sum of all three of them. This means that we can replace the three conditions for winning and losing with just one, like so. To make this even nicer, we can notice one last thing. If the game is a tie, then B plus C plus D is 0. This means that we can represent all of our conditions using the sum of the imaginary components, like this. One last thing we can do to make this formula a little nicer is to define a variable, capital I, which is the sum of the imaginary components. Let us simplify the condition in this way, and we get some very easy to remember conditions. But summing components is kind of cheating because you're not actually working with quaternions. You have to take kind of like a meta stance on it. So instead, let's try to represent I using quaternion multiplication. Since none of our inputs have any real components, we can represent our quaternions like this. And we can multiply them like so. Then we can distribute and distribute again. And now we can use our multiplication rules to simplify. And I've left the diagram on screen if you wanted to try that last step for yourself, but finally we can factor to find the quaternion multiplication formula. Now let's focus in on the real part of the result. Notice that if A2, B2, and C2 are all 1, i.e. if you multiply by I plus j plus k, then you are left with the negative of the sum of the imaginary components, or equivalently, negative I. This means that we can represent I as the real part of the result quaternion multiplied with quaternion I plus j plus k, all times negative 1 to get rid of that negative in the quaternion formula. With this, we can make our equation for the winning player. Recall that the results quaternion QR is the choice of player 1 times the choice of player 2. Now, if we plug this into the gigantic equation at the top of the screen, and it returns plus 1, the player 1 has won, 0 is a tie, and negative 1 is a win for player 2. This means that after all of that work, we have managed to represent rock, paper, scissors mathematically in terms of quaternions. Also, if you want to be pedantic, you can replace the real part using conjugates like so, but I'll leave that as an exercise to the watcher, and it's also not that efficient because it looks terrible. Now, after hearing all of that, the most commonly asked question, which all of my friends asked, is why? Well, there are two answers to that question. The reason why I made this video is because I wanted a memorable way to teach you all about quaternions. But the reason why you would do this to rock, paper, scissors is a little more complicated. Turns out that formalizing rock, paper, scissors like this has a huge advantage, and that it works for any number of objects. That means that we can use it to represent the junk index system or even more objects. All you need is a set of imaginary elements such that all of the elements square to negative 1, and multiplication is anti-commutative, or at least flips signs when you swap inputs. If these two things are true, this system works, and you can create a multiplication system for rock, paper, scissors. And you can use the same formula that we had before for the result with minimal changes. This multiplication is called a hypercomplex algebra, which sounds, well, hypercomplex, but it just means that there is more than one imaginary units with multiplication defined in a certain way. Sadly, the procedure to make a hypercomplex system is a little complicated, and I'm still working on a consistent way of making the system with the least imaginary numbers for any number of gestures, and hopefully I will be able to give you all an update on that later. But now we've finally come full circle. We can represent the junk index rock, paper, scissors system in terms of a hypercomplex algebra. But before I show you that, I have to tell you how you even define one of these systems. Well, to be able to do algebra, we need a definition of what each imaginary number times the other is. For the quaternions, as I said before, you can use this diagram, but since they are annoying and I don't want to keep drawing these diagrams, we'll just summarize it as IJK, which encapsulates the direction of the graph in the way that it's arranged. For example, I times j was with the flow, and if you read it to the right, ij is there as well. Now we have the tools to extrapolate this to higher dimensional systems. But before we can do that, I want to do one last thing, and that's just for simplicity's sake. We want to write ijk as a bolded 1, 2, 3, since it's gonna be hard when we add more letters to keep track of all of them, and numbers are just simpler, but this will lead to some pretty cursed multiplication. Now, the more dimensions you add, the more of these triples you add, right? IJK was one triple, and in higher dimensions, you need more of them. For example, this is the list of triples of the octonions. which are a known hypercomplex system with 7 imaginary numbers. And sorry, I have to stop coloring them, or else, again, I'm going to run out of colors as well. So pay attention to the fact that for every set of 2 numbers, for example, 1 and 6, you will find exactly one triple that has both numbers. And each of these triples represents one of those little diagrams that we had with the quaternions, right? So for example, this 176 triple, you can think of it as a diagram with 1 at the top leading to a 7 leading to a 6, which leads back to the 1. So it tells us 7 times 6 is equal to 1, 1 times 7 is equal to 6, and if we reverse any of them, go against the direction of reading, then we get a negative number. But in this case, of course there's going to be only one, because if two different triples define multiplication for two elements of this hypercomplex algebra, that means there's two definitions of multiplication. So for example, if in this case 1 times 6 is going to be -7, right, since we're going against the flow, but if, let's say, the 145 system had 146 instead, then it would also be equal to -4. And then you could reason that -4 is equal to -7, and that's not good. So only one triple has them, since you can't have two outcomes for multiplication. Now, another way you can represent this is through a multiplication table like this. You essentially take the first imaginary number times the sixth, for example. So what we'll do is we'll start with the row of the thing we want to multiply first, and then we'll go to the column of the right one, and we'll read our result like so, which is exactly the same as our triple predicted. Now, a cool result of this way of writing it is that for each imaginary in a triple, there's one forward moving way and one backward moving way of multiplying it. This means one positive result and one negative result, since one is with the flow, one is against the flow. And since we're only ever going to be adding multiplication rules in triples, this method allows us to keep the game fair, right? Since for each triple you add, you're going to add one winning possibility and one losing possibility. So the game will always remain fair no matter how we do it. Now you can also check this by checking how many positives there are in each row of the multiplication table. But that's going to get really cumbersome really fast. So you can pretty much just trust that the triple system will keep the game fair. Now we can finally go back to why I did all this in the first place, the Junkin deck. To remind you, here is the diagram for the Junkin deck's rock, paper, scissors system in the top right. And at last, here's the corresponding hypercomplex system's multiplication table and triplets. One thing to note here is that the only values we will use are the ones in this box. The ones outside are just there in order to make the math work. The reason we need to do this is a little in-depth, and I can explain it more in another video if this one does well. Let's just say I found the answer in a paper from the 1850s. So for now, we can just think of the extra imaginary numbers as fake or external numbers that just make the math work, right? It makes things a lot simpler. Now, using this system and the same formula as before, it is possible to play a good fair game of rock, paper, scissors, lizard, water, or rock, paper, scissors, lizard, Spock, that's a tongue twister, by just matching each imaginary number to a gesture one by one going clockwise. You can check that this is fair by counting how many positive results are in each row of the box section of the table as discussed before, but I'll leave that to you. I decided to take this to the extreme, and I've managed to make the system of 9 objects. Now, this is definitely not the most optimal way of doing it, and um, yeah, it's a pretty big multiplication table. Now, what you see on the right is actually a graph of what a system like this would look like. And this is taken from uh, a website that I will leave in the comments by David Lovelace. And I'm actually a big fan of his work on this. It was really interesting while I was researching this project, since he actually created a 101 gesture system, even. And I haven't had the time or effort to code something to create the multiplication table for a system like that, but I will definitely do so at some point, and I'll keep you all updated. I'll leave a link to his website in the description as well. But sadly, we have reached the end of this video. I hope you enjoyed and learned something. This video took over 2 years to finish, so please subscribe and check out my other videos. Thank you, and have a nice day.